let's. But this is a little bit beyond the scope of the lecture. So, but it is also instructive to consider special cases. So, I consider the case in which the matrix X is the identity, and I work out the solution of the problem here. Right? Messy slide. But you can so there are 2 points to make. You can compare these to the ridge regression. So here we have considered this problem, right? The case in which you have the identity matrix, and so you have to solve this problem, right? So here you could put a p, and p could be either 1 or 2, or even some number more than 0. It turns out you can solve this problem for every p more than 0. But let's consider p equal 1 or 2, right? So for p equal 2, this is a very special case of ridge regression, and you differentiate, set it equal to 0, and you find, what do you find? So let's do it. You find wi minus yi plus, and let's divide by p, right? So if p is equal to 2, you get plus lambda wi, right? And then you conclude that w is equal to yi 1 plus lambda, right? So as lambda increases, you shrink. That's what the ridge regression does, right? You shrink the solution. So this is yi. The solution is, however, always different from 0, unless provided yi is different from 0. So the one of the lasso instead set the solution to 0 if the absolute value of yi is more than lambda. So it has a very different behavior, the solution. And this is what happens also in the general case, right? So the ridge regression for a generic data matrix shrink the norm, L2 norm, the vector w to 0, but keeping all components different from 0. Whereas in the lasso, set some of the components of w equal to 0, right? And so the reason is that you use this L1 norm, which has many corners. And then so the other point, so there is a very different behavior which you already see in the special case. The other interesting point, which is more difficult, is that the solution of the ridge regression is always unique, right? It's always unique if lambda is more than 0. And so it has a simple formula that we have derived in the course. I think also Mark Webster has described it. Whereas here the solution, if the general case is not unique. And the reason is that this function is not straightly complex, right? However, you can show that if certain things happen, the solution will be unique. And also what is more interesting, you can show, we don't discuss this in the course, that if the data are generated by a certain mechanism, which involves a sparse underlying model, right? So if y is equal to x times some w star, and w star is sparse.
Could you get the background more?
Yeah. Then you can argue, and we'll discuss this in the course, that this estimator, the lasso, the learning method, will go close to the star under some choice with the parameter lambda. Parameter lambda is very important, right? So, but I don't discuss this. So this is more of a statistical results, which it takes more time to discuss. They are very interesting. And so this, so there is a quantitative way you can justify the need for this method. The need is that if the underlying model is sparse, these guys catch it. That's why they call it lasso. Even though the people that proposed this method, they had no clue about why it catches. Then it has been only recently that some people, some statisticians, and there are references at the end, that rigorously proved that, yes, it works. So, but it is kind of a theoretical tower. Right? So you need to assume that the underlying model is sparse. And how do you know that? Right? We don't know the real model. So, but if the underlying model is sparse, if you know something about perhaps the noise, because here there will also be some noise, right? And the noise typically is that you add some Gaussian noise or some noise with some variance, right? If you also know the variance of the noise, then you can show that if you choose this parameter lambda as a function of m is the sample size, s is the sparsity of the underlying model, and sigma, the variance of the noise, and then there is a formula, which I don't remember by hand, but it is of this type. I think it's something like S, and the dimension, right? S log d over n, sigma. It could be something like this, but it is in the paper. So if you choose the parameter, the greater or equal than that, right? Then you can show that the solution, W hat minus W star, has a small bound, right? So you can show that this is less or equal than sigma times lambda. So it's less or equal than this, plus smaller terms. So this is a very interesting result because, so this has been a kind of a revolution in statistics, signal processing. So this also started in signal processing. The reason being is that, so this is M. The reason being that the sample size can be much smaller than the dimension. The dimension can be exponential in the sample size. The sample size can be logarithmic in the dimension. So this has been like, how do you say, a breakthrough, like a shock in the field, because people have realized that you can learn very high dimensional models with small sample size. So the original results were by many people, and I don't know all the history, but I think the breakthrough paper was by Candes, and Tao. And Tao, as you might know, is a very famous mathematician. He's a field medal. He's a genius. I think he got his PhD when I was still in school. And so anyway, he's interested in many other things, and maybe as one of his not hobbies, but one of his main interests, he was working on this. And Candace was very lucky to meet him, probably. Well, I should not say that. But anyway, so that proved for the first time that these results were possible under some completely under some condition. So this is the critique to this stuff that you cannot verify in the real data. So you see, so this stuff works if you know that the underlying model is sparse and something is satisfied. But when we go out and we study real problems, is it true? We don't know, right? So we don't have oracles. So nevertheless, this result tells you that you gain a lot if you use these methods under some conditions. Then there have been some more recent papers which have actually improved these results significantly. And here I mention one by, all these things are at the end, I think. So you don't need to write. By Bickel, Richter, and Sivakov. Sivakov I know well. And this is a very nice paper, nice statistical paper if you're interested in this stuff, but it's mathematical statistical paper. And they've improved the results significantly. And anyway, there are also some books, but very few. So this stuff is still mainly in papers. Right. So here in the course we discuss more intuitively what is the rationale for using these methods and how we solve the problems. But in statistics, you also describe what are the statistical properties of the methods, right? So under some assumption, how close they stay to the model, right? So how close these estimators are to the model. And the bottom line is that they are much better than ridge regression, right? methods which don't exploit sparsity in the problem. Then it's interesting to think why in many applications sparsity is something reasonable to assume, right? And this here there are some debates whether is it natural to consider sparsity, or I will not go into these discussions. So this is stuff that happened less than 10 years ago. So the course is getting up to speed. Right, so you can choose different regularizers, right? And one which I want to describe, which is interesting, is the natural extension of the lasso, which they called. But also you can consider a loss function which uses not a square norm, the square loss, but something else like a logistic loss function for classification, hinge loss for SVMs or other things. So let's call the error term f of w. So concentrating on the regularization term, the natural extension is to do this group norm, right? So where we take, instead of the L1 norm, right, that we have seen before, we take the sum over L, where L goes from 1 to capital N, N is the number of groups, right? And then each of these is the L2 norm of the restriction of W to the group. So this thing is the sum over J, is JL, WJ square square. So you take this kind of mixed norm. So you take the L2 norm within the group, and then you sum the L2 norm. It's a more sophisticated penalty term. So I think the first important part of the lecture is to gain some understanding, intuition, what the L1 norm does, right? And understand that it encourages sparsity. I think this is clear if you work out the special case, right? And to convince that it's a good thing to use statistically, then, well, I haven't convinced you, you need to study these papers. But encouraged sparsity is very different from the L2 norm. So the second purpose of the lecture is to convince that this can be which can be extended, generalized to many other norms or regularizers, which, like this one, which enforce some kind of additional structure. So the model is sparse, but there is some additional structure on the model. And here the structure is that, so here you expect only few groups to be important in the model. So the regression vector which generates the data, you expect it to be to involve only a few of these groups of errors. Right. So when the groups, so J1 through Jn are some subset of the index set, variable index set. When they are, so in this case, when Jn is equal to just the n element, this is just a lasso, right? But, oh sorry, don't look at that. Any question? So if you choose n equal to d and jl equal to l, this is the lasso, right? The L2 norm for the set jl is just the absolute value of wl. So let's do it, right? So if jl is equal to l, then w jl is just equal to the vector which has wl as the only.
Could you shift down the paper? Thank you.
Yeah. So if we consider this case, l goes from the n group is just vector l, method is just the last, so we call it sum. Sorry, this should be D, right? So this thing is equal to L1 now. So so we have the previous method. But it doesn't need to be. And also, what is interesting, so here you see also what could be some application of this. You can also consider the case in which these sets, J1 through Jn, overlap. Okay? Well, originally, in the original paper, by Yuan and Lin, the group were forming a partition of the index set. So the reunion is the index set, and the intersection between every two elements is empty set. So we have 1, 2, 100, right, and everything. I don't need to explain that. But what about if you consider this case? So the first set contains all the variables, all the indexes. The second set, all but the first one, right? The third set, all but the first two, and so on. And the last set contains only the last variable. And here there is a little, before we were calling this D, perhaps. So, sample size is M, number of variables is D or N. This is very interesting in this case, because let's write down what the regularizer is in this case, right? So it's the sum of L to N, capital N, right, which happens to be equal to the dimension N, and then it is, we'll do it step by step. So we have J, this is the definition. So it's the sum, you write the sum, and then I write down what this is. This is the square root, because it's the L to norm, and then is the sum for the index set J in JL, so which is the sum, so if you think about it, J from L to N, right? Or WJ square. Okay? So let's be more explicit. This is the sum. So the first term is just going to be the L to norm of W. The second term is going to be the L to norm of W to Wn, okay? And so on. The last term is going to be the absolute value of Wn. Right? Let's be more explicit. Let's write down what all these norms are. Just to be really pedantic. So the first term is the L to norm of W. So it's W1 squared plus dot 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 Wn square root. Right? This was this guy. The second one is the same. I just remove W1. W2 square plus dot 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 Wn square. And so on. I keep removing terms. Right? So the second last one will be Wn minus 1 square plus Wn square. And the last one will be this one. Right? So this is N. Right? So as you can see here, so what happens here? The last variable, W, so the last parameter vector corresponds to the last variable, appears in every term. Right? Whereas the first parameter variable appears only the first term. So I penalize more the parameter corresponding to I index variables, right? So what happens here is that you try to favor solutions which are sparse, but they are sparse at the end, right? So the last part of the vector is different from 0, whereas the first part maybe will be different. Okay? Sorry, the last part of the vector is equal to 0, and the first part of the vector will be non-zero. Something needs to be non-zero, otherwise you don't predict anything. And you try to favor the non-zeros in the beginning. Right? Another way to reason about this, you can assume that the vector W, right, has its component either 0 or 1, right? And then I tell you that there are only S which are different from 0, right? If you consider the L1 norm of a vector which are only S non-zero, the L1 norm is, what will it be?
Yes.
It will be S, right? Because it's the sum of the absolute value of Wj, only S are different from 0 and they are 1, so it will be equal to S. Now if we consider these, let's call this J, where J is the partition, is this set of sets, right? Then here, different things can happen depending on where the non-zeros are, right? So it's more complicated to compute it, but let's assume that S is equal to 1, just to make it very simple. Now, if W1 is different from 0, it is going to be equal to 1, right? If W1 is equal to 1, all the other are 0. And if W n is equal to 1, and the other 0 is equal to 1. So you see that it takes very different value, the penalty. So the penalty will try to push to 0 the last one, rather than the first one. Right? So it encourages sparse solution, because it encourages few groups different from 0, but right? So let's and you can make other so you can write down, you can choose other sets J which are other meaning, right? This is also called structure sparsity. So
Is there a reason why you took for the last element on the previous slide? When you sum up the norms, you take the L1 for the last element at the right corner?
yeah, because the M2 norm of the vector, which has only one element, is the absolute value. Yeah. So I just applied my recipe. So the recipe that is the regularizer is the sum of the L2 norms of the restriction of the vector W to the group. If the group has only one element, it's the absolute value. So if each group has only one element and they span all the variables, it's the L1 norm. So this is an extension of the L1 norm, which may be a very different solution if these groups for example, like this. So,
Okay.
yeah,
This sounds very restrictive.
it's very restrictive, yes.
Because, for example, if you want to do something with like neurobiology,
Yes.
then you either have to pre-prepare your
Yes.
problem, or just use something that doesn't have.
Yes, so, yeah, you are right. So we use more prior knowledge here than in the previous case. The previous case is like isotropic. So we think that the solution as the model is sparse, but we don't know what the sparsity is. Here we have strong knowledge. The sparsity is ordered. There is one direction along which we expect more sparsity on the right than on the left, something like that. So we have strong prior knowledge. Whether it makes sense, I don't know, but there have been, so all these methods have been applied somewhere. So people have claimed that there are some applications
But
that
are there many places or many applications where this is much more useful?
I don't know. So this is a fair answer, but I think so. But it is very strong, so you can consider a situation in which you have a bit less knowledge. So for example, you could assume you have a tree, right? Because this corresponds more like to a line ordering, right? You can assume that you have like a tree, right? So you have a variable which is more important than all the others. Right? Then if you put it to 0, you pay a lot. Then there are
Lower? We can see what you're.
so you have a tree. That's what that's, yeah. Right? Something like that. Doesn't need to be binary. Something. Right? So but every node corresponds to one variable. So the variable 1 is the most important, should be in the model. And 2 and 3, and so on. So the way to do that is sum over I, so 1 to n, the number of variables. And then you take w. Then for this variable, say this is a variable 3, you take, how does it work? You take the set of descendant of I. So the set of descendant is this subtree. The set is the node itself and what is below it. So that's how you form these groups. So this is, they put that to. So this is a bit less restricted than the line, right? Because the line you have a complete ordering, here you have a partial ordering. Yeah.
This is also extremely useful when you use feature maps, like the ones on the research method that said the polynomial feature map or the assigned feature map, because
Yes, it's a good point.
because
Yes.
you have the more simple polynomials in the
Yes.
beginning
Yes.
explain much of the data,
Yes.
and you leave the more complex polynomials.
Yes, yes, yes.
Which are
Absolutely.
more variable.
Yes.
With a smaller.
So you could assume a nonlinear regression, right? A nonlinear regression, so which is still so f of x is some w transpose phi of x. So it's nonlinear because there are some features, but you know some ordering of these features. So, for example, you know that the higher order monomials are less important than the lower order, right? And then you can use something like this. Yeah. So I think these are used with computer vision. I think there are some papers. But there are many papers in biology that use, in bioinformatics that use these things. Yeah. So this stuff is quite mainstream. Right. So another extension of this stuff is called multitask learning. Right. So this is a little bit different from what we saw so far. And next week we'll discuss it a little bit more in detail, in the sense that we have, right, so now we have more than one regression problem, we have many of them, right? That's why it's called multitask. So there are multiple linear regression problems. Or they could be multiple binary classification, but let's look at multiple linear regression. Right. So each of them is, there is a vector W of T. It should be T. Right? So I collect them in this matrix capital W. So the columns of the matrix are the different regression vectors. Okay. Then there are nice applications. So we could think, for example, that could be that each linear regression, so the index T, which goes from 1 to T, refers to a user. So in the context of user modeling, so it would be a person, right? And the regression problem is like what that person likes. So like X is a product, WT is a set of regression vectors which describe the preference of that person, right? And WT, right? WT transpose X is the value of the function for the T user on the input X, which says how much the person likes that product. Right? So the larger it is, the better. So and we have data for each of the different of the users for each of the regression problems, and we want to fit. We want to learn this matrix. We want to learn all the different regression vectors. Okay? So this can be seen as a single regression problem with some structure sparsity. That's what I want to describe. So we see that what I just described before applies here. So we can consider the following regularizer. Where, so if you like, all the parameters form a matrix, or if you prefer, you can concatenate them and form a big vector. This is just a notational issue. But the regularizer takes the sum of the L2 norms of the rows of this matrix. So this means that you have a way to partition the elements of the matrix, right, along the rows. Right? So in the previous slide, we were considering the regularizer. Yes, this one, right? Now I'm going to rewrite it. It was the sum over sum over L from 1 to L, and then it was WJL 2. Now W here is my matrix, right? And JL is a set of all elements of one row. L is the row. Okay? I'll go here. Bit awkward to call JJ. So you see what I'm saying, right? So we have W, right? So this is the first set of variables, second, and so on. Right? So here, so you try to solve this problem. You have an error term, which is the sum of the errors across all data points. So you sum over the users, you have a task, and for each you have a sum over the sample size, over the samples for the task. I assume this to be independent of t, but it could be mt, if you like. So it could be different sample size per task. And then the regularizer says that what it says is that only few of these should be non-zero. So this is the intuitive rationale behind the penalty. So which means that only few variables are different from zero across all the regression problems, across all the tasks, right? So to understand this, you need to digest mainly the notation and then realize that it is the same as the previous one. So what this does is to say that that the regression vectors are kind of aligned, right? So if this is the W matrix and this is W1, W2, so the columns and the W's, right? So here the dark means 1 and light means 0, right? You have that there are only 2 non-zero rows, right? And so there is a structure sparsity, which means that all the regression vectors have only 2 non-zero variables, 2 non-zero components at most, but here there is 0, right? And they are aligned, right? The sparsity pattern is aligned. So the location of the non-zeros in each vectors are corresponding. Right? So they are in the same position. So this is an application of this group lasso. Actually, with non-overlapping group in this case, so it's particularly simple. So this has been applied quite a bit. So this is an example where this stuff is used. And I will elaborate on that, but it's just to be more explicit. Here you see that. So here you just to have an illustration of what is the meaning of the different regularizers. So here we take a matrix, right? So I don't know, so there are T times N, or maybe D. So there are T different regression vectors and n-dimensional each of them. And maybe this is, I don't know, no idea, it could be 16 times 13, right? So this is like a big vector which is whatever it is, 200 or so dimensional. And here I suppose that there are 29 components which are different from 0. So equal to 1, and all the others are 0. Right? Now if you you can look at different penalties. So the first one, you look at how many rows are different from 0 in the matrix. And here they are all different. Here there are 5, and here there are 2. Right? So this one is very much simple. So the row sparsity is very much simple. So you have a very simple model, which is in the sense of row sparsity. And here what you see is that this group lasso regularizer, right? So the sum of the L2 norm tends to follow the row sparsity pattern. Right? So here is 19, here is 12, and here is 8. Right? So remember, G of W is the sum of the L2 norm of the different rows of the matrix W. And I guess it works, because you need to count, you need to take, you need to say how many are here. Maybe there are, I don't know, it should be 9. Square root of 9 is 3. Maybe here there are 16. Well, it doesn't work, so we need to work it out. So, but let's say that maybe there is an error here. Okay. Right? But so the penalty here in G of W is the sum of the L2 norm. The last one is the sum of the average value. And here there are always 29 non-zero put in different locations. So the L1 norm doesn't discriminate the different locations. It just counts non-zero. It doesn't discriminate between different configurations. So here you see that if you consider as your learning method, the one which uses this, it biases more your solution towards vector of this type, right? So if the data happens to be generated by vectors of these types, by matrices of these types, then the method has an edge, and it will work better. So you can make that, you can show that that is true by some quantitative analysis. Right? So, any questions? So, this is interesting because so say you have the people in the room, right? So there are many more, and let's say that people are all similar taste. Right? So you show them some products, and they all look at the price of the products, and then they look at few other features, variables which describe the product. So for example, computers, you look at the price, and people tend to look price, screen size, and the RAM, right? The speed. And that's it. This is all you care about the computers. And then maybe you weight these three different variables differently, and then you decide, but typically you will look at the price is not too high, compare, so something like that. Now, if this is true, then what you can show that even if you only have a very small sample size for each task, for each user, so maybe 3, right? One. Right, so you have only one. So even if the person only looks at 3 things, since you have only one sample, you cannot understand how he decides what the linear regression is, right? So the linear regression is W transpose X, right? And there are only, W is maybe 100-dimensional because there are different irrelevant variables which describe the product. Only 3 are important in determining the response of the person, but you still need a little bit more than 3 samples to identify the vector parameters. Right? Now, even if for each person you only have 1 or 2 samples, but then you go around and you ask many people, right, how much they like this computer. Right? Then you can put then you can use you exploit synergies between the task to find where the location of the non-zeros are. Right? So the non-zeros are only these 2, the third one in this example, and it works. So you can show that you can improve the estimation of all the different. So, and the way you do it is by using this regularizer, right? Which is a special case of the group lasso. So this is an application of the group lasso. Yeah.
And the assumption being again that the model is sparse.
Yeah. But, yeah. This thing also works if the model is approximately sparse. So the assumption doesn't need to be so strong. So most of the coefficients must be concentrated on few components. There can be a little tail of. So, and now there's another interesting problem which is called collaborative filtering. So it's very similar to what I was describing here with the users. And here you can assume a different model, which is you can assume that the regression vectors, so when they form this matrix, the matrix is low rank. So this is also something which I studied a lot. So in this case, you study this problem. You minimize the error subject to a rank constraint, or perhaps rank regularizer. So the way this works is as follows. So you have a matrix, W, right? And this matrix has physical meaning. So the columns are the users, like before, and now the rows are the products. So now I don't describe a product by some variables. I don't do a linear regression, but I directly describe it by an index. So the rows index products. So it could be like the movies. So there's Netflix, this data set, in which you have, say, several thousand users, 500,000 users, I don't know, and several thousand movies. So it's a huge matrix. Okay, huge matrix. And here, an entry of the matrix, so the entry, we could call it IJT, says how much movie J is liked by user T. So that's okay. And we sample, we know only few entries of this matrix, say 1%, 2%, something like that. So the question is, can we and maybe we know it with some noise because people don't always behave the same way, but usually, I don't know, if you like Pulp Fiction, or you tend to like it all your life, or there are some issues if you want to really use this stuff in practice. People also change their mind, right? But let's just assume that if we repeat the experiment all the time, we will get up to some noise the same answer, right? So we assume that there is an underlying ground truth, which matrix W star, right? Now here it doesn't make sense to assume that this matrix has only few non-zero rows, right? Because it doesn't make any sense. Right? Because WJT equal to 0 for many J. However, what we can assume is that there are only a few principal components in this. Principal components of the columns or of the rows, right? So which means that there's a different way to explain that, but so one way you can say that there are only a few factors which explain people's mind, right? So another more mathematical way to say that is that all these, so the columns of the matrix describe what people like, right? Because the column, right, goes down. We have movies, we have users. Right? If I take one column, I have a complete picture of what that person likes, right? So the assumption here is that all these columns can be well approximated, or can be written as a linear combination of few basis vectors. So this is the assumption of low rank, right, of a matrix. the context of PCA, you say that most of the variance of these columns is captured by only few directions. Right? And here I say that it is exactly captured by only few directions. But in this case also, you can show that doing some structure sparsity, but here it's not exactly sparsity, right? It's low rank. Using some low rank assumption to bias your solutions allows you to learn the underlying matrix with less measurements, with less examples. Okay? So what you do, you consider this problem, or some modification of it, which involves what is called the trace norm. This is more sophisticated. So the trace norm is the sum of the singular values of the matrix. So we're studying single value composition. So the end problem is this one. Right? So and here the sum, right, is from 1 to m, where m is the number of entries of the matrix that you know. Right? So this xi is this is a bit complicated. I apologize. It's something like ERI PCI transpose. But so this is just to say that the error term is a sum over I, and then you have yi minus w rho I and column I. Right?
I don't want to be boring. Could you put it down a bit?
Oh yeah, so you are not boring at all. I am I perseverate. So, okay. So, but is it clear what I mean by this? Right? So, I take the ith sample is obtained by choosing one row index, one column index, row, one movie, one user, and then I get my output yi. Right? So the inputs are like pair of indices, which refers to moving product, and the output is the preference, like is the. And it could be 0 or 1, like, not like, or it could be 0, 1, 2, 3, 4, 5, like how much you like it, like or and there are variations of this problem, so which one can make. For example, you could show 2 movies, and you can say you like more this one or the other one. So, and all these variations are important if you care about the real application, but they are not so important if you want to understand more the general problems, the general underlying problems. So I avoid going too much into technical practical details. But here the message is that this also connects to this kind of sparsity methods, right? And the way it connects is that the regularization, the regularizer, and again the solution is the regularizer is a norm, so you cannot set the derivative equal to 0 because it's not differentiable, so you need to compute a subgradient. It's like the optimality condition. So here you can show, for example, if you consider the special case in which you sample the whole matrix. So now y is the whole matrix and w is the variable matrix. So this is like in the case of the lasso when you take the identity matrix as the matrix X, right? Then you can solve the problem. This we have studied in mathematical programming research method, which we are taking that course, and I think, well, kind of. So here you can show that the solution is low rank, and it is given by this formula. So u and v are the singular vectors of the matrix Y, and then the singular values are obtained by applying this soft thresholding operator to them. So it's the matrix extension of the solution for the lasso. And the way this is to you use some inequality, and then it's a von Neumann inequality, and then the result falls. Let's skip that. Okay, I can tell you this is not the main point. The main point of this is to show you that there are other regularizers which make more sense in the context of collaborative filtering, or also in the context of multitask learning. You can use this one. which leads to a more sophisticated notion of parsimonious model of sparsity, right? So here, the sparsity in the sense of low rank. All the methods that we will describe, I guess, this week a little bit, last half an hour, apply to this method, apply to these regularizers. Okay. So they are related, different, but the same machinery applies to find a solution.